So today we're going to have a look at structure solution for aluminum vanadium oxide. We're going to have a look at the XID pattern, and we're going to try and solve the structure by charge flipping. And we're going to hopefully simulate what it would be like if you was to get a novel material and what to do to try and solve the structure. So we've got the D pattern here. This was taken on a Brooker X-ray diffractometer, and the first step is usually the hardest step. So the hardest step when it comes to solving new structures is finding the space group and the symmetry. It's by far the hardest thing to do, but once you've done that, it makes it a lot easier to find the final solution. So as a start, let's say this was your novel XRD pattern, the first thing that I would do is go to literature and see if I can find something that is similar, where the peaks might line up, not necessarily the intensities, but as long as it's got the right peaks, especially the most intense peaks at the right 2 theta, that's an indication that they're probably the same or very similar space group. So after you've done some initial looks into the reference structures, I close that, you might find that it strongly resembles the iron vanadium oxide phase. You can see here the patterns are very similar, not exactly the same, but very similar. And so what you would do now is you would take the space group and the unit cell parameters. So let's say, where is it now? So now we're going to run a Pauli extraction. So we want to extract, we're going to extract an A matrix file. However, you can also extract the HKL intensities. I just like doing A matrix files because it works for charge flipping. And so we're going to go set up our Pauli input file, and I'll be back in a second. Okay, so in our Pauli input file, the first thing we're going to put is the R factors. I'll save it after. Let's put a space, and then so it's called raw AlVO4, and then it's copper KalF1. So that's these are the instrument files. So we've got the wavelength, polarization factor, and you can find these from the scan file. if you've got a .raw file. Simple axial model. And 0 error. Okay, so then we can fit a. It's probably best to just do this. We can also do the background on GSAS, but for now, let's just do a Chebyshev polynomial. And then we've got the space group is P-1. So let's put that. And the unit cell parameters, A is equal to 6.719, B and C, and that's alpha. And gamma. And then let's put this as well. So we've got our peak shape and our output for the charge flipping, which is the A matrix file. And so I'm going to save this and I will run it in Topaz in a second. Okay, so we're on Topaz. Let's set the input file, and this is the one that I just made. And let's run it. Okay, so there's something wrong. Okay, I'll fix this 1 minute. Okay, so I missed a bracket off of the instrument file. So let's save that again. And let's come to Topaz and launch, set the input file. And apparently we've got something else that's wrong. Let's try that again. And this is also really wrong. Okay, I will go and have a look at the file and I will be back in a second. Okay, so here we are. this is the problem that we had. So we was using iron vanadium oxide as the unit cell initial gas parameters. So these are what we started with, and you can see that some of the peaks are not being fitted, but you can see that there is reflections, however, they're almost just shifted, like in the wrong place. And it made me think, well, this is the unit cell for iron, but the structure that we're refining is aluminium. And so I went to a useful website. Here it is. And it's called Shannon Radii. Don't know. I just typed Shannon Radii. And then if you look at the size of iron, and it's either going to be in tetrahedral or it's going to be in octahedral. So if you look at iron, you can see it is larger than that of aluminium. And so we're probably going to see a contraction in the unit cell parameters that's shifting the peaks. And so we need to move these reflections so that they line up with the pattern correctly. Now, what to change it by, there is really no rule of thumb. I'm just going to change it by 0.2. So let's change it to this. We'll change this to be that. And we'll change this to this. And now if we run this, hopefully these peaks should clear up. So let's run. Yeah, so now you can see, we'll click no for now. All the peaks have been fully matched and all of the reflections are lining up correctly. So we know we've got the right space group. Now it's just a matter of finishing this poorly, and then we'll set the charge flipping input file. So let's have a look at the output. So we've got the background here, 0 model, all the instrument data. You don't actually need this for charge flipping because it's already made. Oh, that's one thing I needed to do. I needed to change the name of this to number 2. And let's run that again. No. Look at that output file. Okay, so our refined unit cell parameters are a lot better this time on the unit cell angles. Okay, so now we've got our A matrix 2 file, and we're going to use this for charge flipping. I'm going to set up the charge flipping file, and we'll run through some of the things that you need for the charge flipping run, because it can be quite tricky sometimes. Okay, so I'm going to set up the charge flipping input file, and I'll do it here. And as we go through, I'll try and find what it means in the TOPAS manual. Although this TOPAS manual, as good as it is, I don't even know if this is the right manual. Is this the right manual? Let me see if it's the other one. Right, I've got the right reference manual now. So this manual by TOPAS has the all of the code, and I want to say it tells you what it means, but there's some things that like it sort of tells you what it means, but it's not brilliant. It's okay. I've read it through, but it's I don't know. I think it would be easier if I worked for Brooker and I had someone explaining it whilst doing it instead of learning it myself. But we're gonna build the charge flipping file anyway. So the first thing that we need is a section for the macros. And this is macro and then we're just going to set this to let's do 20,000 for now, and then we want the iteration number to also be 20,000 so that it will finish after one cycle. So this macro, let's see if I can find it. No. What about if, or just NR? No, because it's a macro that I found in the TOPAS. Like they have some tutorial files that you can look through, and what I think it does is it starts at 20,000 and it puts in. Let's say you want to ramp something. So one of the things that we might use could look like this. So this is telling the charge flipping procedures to obey the symmetry on a ramp. And we're going to set up all of the ramps so that they're all ramping from 20,000. And then they sort of slowly all converge to the final solution. And hopefully that final solution should be what you want if you set up the other things correctly. So let's get rid of this for now. And the next thing we're going to input is let's tell it it's a charge run, and then we need to put a file. So let's say charge flip in. So we're going to do the A matrix file, and then it's called AlVO4. I think we called it 2. I'll check that. Dot A. Okay. So now we need. Okay, so now we go to the output file from the poly, and we need these values, and above it we're going to put the space group, and then you can't refine the unit cell parameters whilst you do a charge flipping run. So, okay. So now let's call this. Okay, so there's lots of things that we can do now for this charge flipping procedure, and it, from my experience and from what I've sort of read and seen, so we're gonna add parameters to the charge flipping run, and the more you add, the more so narrow your search becomes for, and you start restricting things from, like, you're restricting how much it should flip the charge, and some other things. So I'll run through what we're going to use on this run, and then I'll also include some other ones that I've seen that you could use and play about with. But it's tricky because to find any information on some of these things, it's quite difficult. Um, some of it is said in the technical reference file, but the custom ones that they use for some of the Booker files can be quite complicated. So let's start with this one. So all of the weak reflections on TOPAS. So despacing 1.19. So that's using all of these. So we're going to add this into our file. We'll change it to 1.2, and what this does essentially is gets rid of any sort of weak reflections that might arise during the flipping procedure, and it should make your electron density cloud more clearer. So then we're gonna put this one in. No, this one is a complicated one. Let's see if I can find it. Yeah, so the EOL sphere, it changes the size of the sphere around the atom, the density. Yeah, so you can see here the amount of perturbation and how much to ramp all of these factors is quite important. And if you have too much, then it won't end up finding a solution. Or if you don't have enough, it won't end up finding a solution. And so we're gonna slowly ramp it down. We're going to start from a high value, but we'll start from a small value and we'll see what it gives us for a small value as well. So now, if so, the next thing we're going to put on is this. And so it adds the weak reflections that it finds in this one. On a ramp. And you can see for poor data quality. And then the next thing we're going to do is flip regime. So the amount that you use these is, so the flip regime modifies the electron density further, and it is ramped between 1 and 0. And because we're setting all of this value to NR, it's going to ramp with this macro. Then we're going to put the symmetry obey. And these can also be changed. You could change this to 0 and leave that as 1, and then keep the ramp on. And then another optional one is this one. So symmetry obeys 0 to 1, defines find origin. So it finds the origin and will attempt to find the symmetry as well. And so it uses the equivalent positions of the space group and will move the atoms according to the symmetry. Then we've got find origin, so we don't actually need this. And then this one, which is used for poor resolution data, and helps to clear the electron density map. There we go. So it sharpens the electron density. I think they recommend to just always keep it at 0.3 and 30. Okay, so the next thing we're going to put in is for the, this is just the spacing on the grid when it shows the electron density. So I think if you want it to be more detailed, you would put this down towards a smaller number. So we'll try 0.2 because I would do want to see it in detail. Then we're going to add this, and this is just the atoms and the amounts of the atoms and how many it should, not how many atoms, but I think how often it should pick a new solution. So this can be changed to be like if I change this to 1,000, every 1,000 cycles of electron density change. So it changes two things. It flips the electron density, and then it moves the atoms about to try and match that density. And so you want to flip the electron density really, really fast, but maybe keep this not as fast. It is on every one cycle, just because sometimes it can take a long time to find a solution, but if you leave it on one, it might speed it up. So that is, I think, everything we need for the flipping procedure. Let me quickly show you some of the other ones. So I'm not going to go through them all. So again, we've got a string calculator sphere, symmetry obey, ramp, find origin, min-grid spacing, pick 1,000 this time. Symmetry obey, and then it's saying something to do with the weak reflections and removing them weak reflections from the electron density map. And then this is the fraction of the actual electron density that it should flip. So this is an important parameter, and if you the closer to 1 you have it, the more of the electron density is going to be flipped. And then this is so if you find a solution, this result from the card flipping, you can set the initial phase for another run to be equal to that solution, and it might find a better solution from that quicker. And then some of the others, you can include a sine wave function to the way it flips the density, and then the resulting charge flipping procedure oscillates in a sine wave. Some other ones here, but yeah, so you can copy that if you would like to play around with it, but we're not going to use it. So I think we should try this. There'll probably be an error somewhere that we might have to fix. But I'm going to save this and then open it in TOPAS. Okay, so I have a problem here. Let's see if this works. So now it's going to run the charge flipping procedure. For how many cycles did it say? 20,000 cycles. So you can change the electron density. You can scale it. Click 2-part and it goes a bit more dense. But slowly, as it reaches towards 20,000, this should slowly go towards maybe about 0.5, 0.6. But we're going to try it with a smaller ramp number, and see if, so let's just try some, see if we can find a meaningful solution in 1,000. Okay, so it's finished. Let's check out the structure. So this is obviously wrong. Now you've got two aluminiums bonded together, vanadiums bonded together. So now we'll increase the ramp rate and the amount of iterations. So let's just go 5, see if we can find a better solution. So the result wasn't great again. So I'm gonna run it now, but I'll run it on. Pick one. See if that works. And I'll be back once it's done. So the final result again was wrong. You can see that it's more of a linear decay, which is a bad sign. You want it to be maybe for about 2000 cycles, stay up and then drop. So I'm going to have a look at the charge flipping input file and I'll be back after that. Okay, so changed a couple of the things. So we're going to do 10,000 cycles. I changed the minimum D spacing to the smallest D value from the XRD pattern, and change this back to 0.3, and I'm going to run this now, and we will see what it looks like. I will start the video again when it gets close to 10,000. Okay, so after a lot of a lot of charge flipping, we've ended with this, and this is our final flipped structure. You can see the vanadiums are all in tetrahedral, and the aluminium are in octahedral. Or two of them are. And one of them, so this one here has 5 oxygen bonds, and this one here has 6 oxygen bonds. And if we look at the structure, we have a aluminium with 5 oxygen bonds, and we have a aluminium with 6 bonds. All our vanadiums are in tetrahedral. And so we now have the final structure. You can make the electron density look pretty if you wanted to. Something like that. And now this will be ready for revealed refinement. So to get your atomic positions, we're just going to reduce this for now. And what we want is we want width symmetry, and we want pick, and then here are all the atomic positions. I would suggest copying this and pasting it into something like ChatGPT, which can parse it and put it into the correct format for revealed refinement. We're not going to do revealed refinement of this sample today, but that is how you that is how you charge flip from an initial structure without knowing anything about the phase. The final charge flipping procedure script was 5,000 iterations, ascended first 0.8, we turned off find origin, and I put this on 180 instead of 90. Okay, thanks for watching, and I'll upload some more videos on charge flipping and refinement in the future.